Okay.
I will start on two computers. Andrea is left. Okay, very good.
So I hope you can see the screen.
We can see your screen. Thank you. Yes. So it is a great pleasure to introduce you our last speaker of the afternoon, Felipe Pacheco-Vázquez from the Institute of Physics of the Autonomous University of Puebla in Mexico. And he's going to talk to us about compression of granular columns and subsequent relaxation processes for different types of grains. Felipe, it's a great pleasure to have you here. Thank you so much for accepting our invitation. You can start your talk. Thank you.
Okay. No, in fact, I want to thank you, Yuri, for the invitation to this workshop. It has been very nice to listen to all the speakers. And well, I'm coming from the Autonomous University of Puebla. This is a picture of the city, and this is the campus. It's a city that is 2 hours by car from Mexico City. And I have a laboratory that is called Brains Lab, where we perform experiments on granular materials and physical fluids. So let me just very briefly show you some videos of the recent work that we have been performing. For instance, we have studied the differences between the impact of spherical projectiles that typically people studied versus projectiles with protuberances that produces ray systems in order to try to understand the formation of ray systems on the moon, for instance. We have also studied air entrainment and granular bubbles that are generated when you just pour dry grains into water, and the grains deform the interface. And as you can see, they produce air entrainment that generate bubbles. The grains are attached to the interface to the surface of the bubbles, generating these granular encapsulates. As you can see in this figure, the bubbles are covered by grains, and they are very stable because, in fact, you can see here that there is a grain between two air bubbles, and this grain avoids the coalescence of the bubbles. Also, the grains that are covering all the particle basically avoids the coalescence with the interface. So for that reason, the particles, even when they are very large, of the order of millimeters, the bubbles are very large, they can be very stable during several weeks, in fact. We have also studied, this is the most recent work that we have published that is related to the collision and coalescence of Leidenfrost droplets. So you put droplets on a very hot pan to have Leidenfrost effect. So droplets that are levitating with some vapor. But you can see that for water, there is a direct coalescence. For ethanol, also there is a direct coalescence. So droplets of the same liquid coalesce directly. But when you have droplets of different liquids, for instance, water and ethanol, you have a nice bouncing dynamics. So we try to explain these dynamics by why the droplets don't coalesce when they are miscible by analyzing or by taking some picture like this one, allows to observe that you have this droplet that is, for instance, water at 100 degrees Celsius, and there is another droplet that is ethanol, and then it's at about 70 degrees Celsius. So the water drop is very hot compared to the ethanol drop, and the ethanol drop then experiences also the Leidenfrost effect with a larger water drop generating this vapor layer. So the vapor layer practically avoids the coalescence. But I'm not here to talk of this fluid dynamics. I choose a topic that is closer to this mechanics session, and it's about the compression and relaxation of granular columns composed of different kinds of grains. So we are going to talk about brittle grains. We are going to compare it with rigid glass beads, dust agglomerates, and magnetic repelling particles if there is enough time. So if you go to the literature, and you will find that the most typical plot that is analyzed during the compression of soils and sand is the void ratio versus the vertical effective stress. So basically, you put a granular sample, you compress the material for a given load, for instance, 10 megapascals, and then you observe the change of the unloaded material to the void ratio that is reached with this stress. No? But which is important in this kind of plots is to characterize the final state of the system. But more recently, people have been interested in measuring the dynamic evolution of the stress during compression of the granular sample. So this is, for instance, a work from Itai Einab's group in Sydney, Australia. they put some grains inside a sample. They put brittle particles. In fact, it's puffed rice, a cereal. They put the particles inside. They compress from the top with a piston, and they measure the force acting on the piston and also the force acting on the plate at the bottom. So you see this in this plot. You see the force how it increases in time during compression. But something interesting is that there are apparent periodic spikes during the compression. Yeah, and well, they explained these spikes by taking pictures, lateral pictures of the compression, and then by constructing these digital image correlation vector fields that basically gives you what particles move from one snapshot to the another one. So they, by the difference of the position of the particles, they can obtain what particles move. And you can see here that the particles basically at the bottom are crushed during the compression, producing that all the particles move at the top, and then this part becomes solid, and the crushing happens at the top, more at the top, and then this compaction band travels upwards through the granular sample to reaching the surface of the granular bed. And when it reaches the surface of the bed, the compaction band again appears at the bottom, and then it also travels, producing a periodic spikes on the force versus time. In fact, this spatial temporal plots show that this is periodic for the case of smooth lateral walls, but when they put root lateral walls, they observe an erratic compression process. So we wanted to see what happens if instead of having these brittle particles, we have hierarchical granular material. So hierarchical granular matter basically is when you have a large particle that is at the same time composed of smaller particles of the same material. So there are binding forces like capillary forces, electrostatic forces, or van der Waals forces that join the grains together to form a larger particle. When you put a lot of these particles together, you have the hierarchical granular matter. So there are two different length scales in the system. The length scale of the tiny monomers, as you can see here, the small grains in this picture, and the length scale of the large dose particle, in this case. In nature, you can find it, for instance, ants, they build this kind of granules by putting a small pieces together to form a larger granule of hierarchical granular matter. And hierarchical granular matter is everywhere. You can find it in different scales, from asteroids and planets up to the everyday life when you can flower of a mud ball as the one shown in the previous snapshot. Okay, so to characterize this, we started by characterizing the smaller particles. So we took tiny glass bits of the order of 5 microns. So they are basically powder. They are 5,000 smaller than the size of the cell. So there is a large difference between the ratio of the cell and the particles. And as you can see here, the force, when it's measuring, as you compress with the piston, you measure the force. You measure the force acting on the piston as a function of the piston stroke, theta, and then you observe that it increases non-linearly. And in fact, this linear log linear plot shows that the force increases more or less or nearly exponentially. So there are no peaks or sudden drops in the force for the tiny glass bits. But if you increase the size of these bits, so this is not hierarchical granular matters, these are solid bits. As you can see, the force, for the case of 100 microns, there is still basically continuous increase of the force. But when you increase the size of the particles, you can observe that there are sudden force drops. So these sudden drops of the force load are related to the fact that you need to apply a larger force to move a particle at a distance that is close to its diameter to arrange the granular sample. So this is why you need a larger force drops as you increase the particle size. But what happens for hierarchical granular material? So first we fabricate our material. So we put the tiny glass particles of 5 microns in a rotating drum. Then we add some water, we spray water. And then by rotation, we induce the formation of these agglomerates. So these agglomerates, in fact, are very, very porous. They are soft and fragile, so you can deform it, but there is a point when they break. So the porosity of these grains, the packing fraction is about 0.3, And considering a standard packing fraction of 0.6 for the granular material, we will have that the bulk packing fraction of the granular column is about 0.18. So it's a very porous granular column. And we are going to compare the results with the glass beads. So for the individual dust particle, we put the particle in the compression machine, and then we compress with the press until reaching the failure. So you can see here the fracture that appears during the process. So in this plot, this is the force as a function of the stroke, and you can see that the force, the resistance to compression increases basically linearly until reaching a maximum, at which moment the failure occurs and the force decreases abruptly. So if you divide the force by the cross-sectional area of the particle, you obtain the stress, and if you divide by the strain, the piston stroke by the diameter of the particle, we have the strain. So we build these stress-strain diagrams to obtain the strength of failure, that is about 16 kilopascals, and the strength rate, that is about 6% the size of the particle. So when the particle is deformed about 6% its diameter, the particle breaks. This is of the order of the strength to break of the particles. So now we put the particles inside the container. So we have here a sample, and then we compress from the top. Here you can see some snapshots of the compression process. You can see that some grains start to be crushed at the bottom, for some particle sizes. And then we measure the force as a function of time. So here, time equal to 0 is the time at which the maximum force is reached. Negative times corresponds to the compression phase. So it's just for reference. So here we are compressing up to the moment we reach the maximum force, and then the piston stops, and we start measuring the relaxation force. So there are two stages: the compression force and the compression phase, and the relaxation phase. So during compression, something interesting is that if you plot the force as a function of the piston stroke, you will observe that there are oscillations, these undulations of the force load or the resistance to compression, and that that there is independent. The mean value of the force is basically independent of the compression rate. So we went from very low compression rates to very high compression rates, from micrometers per second to millimeters per second. And you can see that the mean value is basically the same, but what increases is the size and wavelength of the amplitude of the oscillation, the amplitude of the oscillations. So for small compression velocities, you have very large oscillations, while for fast compression rates, you have very small oscillation. So to understand why there is this difference, we took also digital image correlation analysis by comparing two consecutive frames from videos taken from the front lateral view. And you can observe that for low compression rates, all the sample is compressed. The red means that all the particles are moving very fast, and black means that they are not moving. So as you can see here, there is a moment when all the particles are moving, and in the next frame, they basically are not moving. But then you continue increasing the stress up to a moment where, again, all the particles move. So there is this periodic compression where all the particles move inside the granular sample. While for large compression rates, what we observe is that the compressed material is basically close to the piston that is at the top of these snapshots. So only there is a local compression close to the piston when you compress very fast, and for that reason, the amplitude of the compression is smaller. Well, this qualitatively allows to describe what happens during the compression. Then we try to quantify the increase of the force versus stroke. So if you put this in a log-log scale, you observe that it's basically linear. So this is a power law growth for the mean force. And also, if you subtract from the force measured with the piston, that is the blue line, the mean force, that is the green line, then you obtain the oscillation. And then from the envelope of the oscillation, we can, we observe that also follows a power law, the envelope that is this dashed line. And and then we found the exponents, the coefficients f star and the exponent alpha and alpha zero from the analysis for the different compression speeds. So here we show the exponents as a function of the compression speed, and you can see that the exponent is basically of the order same of magnitude of 2.4 for both the oscillation and also for the mean growth. But the coefficients, for instance, for the mean growth, or this is more or less constant, so the order 10 to the minus 2, as the red line indicates. But for the oscillation, there is a dependence on the compression speed. So the mean value doesn't depend on the compression speed, but the oscillations depend on the compression speed, as we observed previously. So there is this dependence. So we can build this this function that depends on the oscillation, the power law for the mean value, and the power law for the oscillation with this oscillatory compression oscillation. So we also estimate the value of lambda, that is the wavelength of the oscillation, by analyzing the peak of the wave number in the power spectrum, as the one shown here. So we obtain the power spectrum of this of the envelope of the oscillations, and then from the maximum peak we obtain this value of lambda, and this was plotted as a function of the compression speed, and also we found a dependence on the compression of B, the compression speed. So by putting all the information together, we basically say that the dose particle, the F versus theta, the compression versus the piston stroke, increases as a power law multiplied by this term that is related to the oscillation dynamics. So we performed the same analysis for the case of glass beads. And we found that, well, for this case, you can notice that instead of the undulations, you have these sudden force drops during the compression, and then you have the slow relaxation that is continuous and smooth, as in the previous case. So from the compression of glass beads, we performed a similar analysis, but in this case, we found that the force increases with theta following exponential dependence from this semi-log plot, and then, well, this is exponential instead of the power law that we found for those particles. Okay, so from a similar analysis, something that we can say is that for the case of those particles, you have a power law increase, while for the case of glass beads, you have an exponential increase. So we were at the moment where we were working on this, we were also working in the compression of in the discharge of a silo composed of magnetic repelling particles. So we wanted to study what happened for the case of compression and relaxation of magnetic repelling particles. And this is a work that we are performing in collaboration with our host, Yuri Dumares, and also with his brilliant student, Jorge Modesto from the University of Brasilia. And then this is a different kind of material. In fact, this is a two-dimensional system where we put the grains. But the important thing here is that the particles are not touching between them. So they are the magnets, cylindrical magnets, that are introduced in a helio cell with the magnetic moment pointing perpendicular to the surface of the walls. And then you generate, there is a repulsion between the magnets. So we put the particles inside the granular bed, and then we compress from the top with a piston, as in the previous cases, to see what is the difference with the previous experiments. And this is an example that we obtained. So this is a compression expansion cycle for this material. And as you can see, the piston descends, pushing the particles, producing a rearrangement of particles that is very easy to see here because the system is two-dimensional. So, and then you can practically crystallize the system. So the final state is almost hexagonal close packing, as you are there. Then we stop there, and then we start expanding the system by moving the piston up, as you can see there. So the magnets also have repulsion with the piston because this is also a magnetic bar. So there is repulsion also between the particles and also with the walls that are around and with the piston. And we measure the force versus the compression versus the piston. So it's a similar experiment to the previous cases, but here with this granular material that is composed of repelling particles. So we studied two different configurations. The first, these are experiments. So this is the standard packet bed. So we have the particles, and this is a loose packet bed where the particles are more separated at the beginning of the process. So as you compress, you reach the maximum compression that, as you can see, it's practically, you cannot distinguish from one to the other one. And in fact, during the expansion phase, you can notice that the final configuration is very close to the final configuration of the loose packet bed. So there is no information about the initial packing conditions in the final packing state. So there is an important hysteresis in the system. So to characterize the system, we follow the density profile. So here, this is the video that we are going to move the piston that corresponds to this line. In fact, the vertical direction is in the direction of this arrow, the red arrow. So we are compressing the material in this direction. And this line corresponds to the density profile, so in a gray scale. So this means that there are particles here, there are no particles. So it's basically this line where there are no particles, there are particles, no particles, etc. And you can see this oscillation. This is the reason why you observe the oscillations, because the particles are not touching between them. And then if you start pushing the particles, compressing the grains, you observe that the density profile increases close to the piston. And then there is a density inversion because the maximum compression is now at the top close to the piston, while there is a minimum density in the middle of the material, so around here. And then if we expand the system, we observe again that there is a decrease in the compression to reach in the final state. So to characterize the system, we analyze these density profiles. You can see here that for the standard packet bed, basically the density profile follows a hydrostatic dependence with zeta, or with y, that is the vertical position. And there is the density inversion in the maximum compression test. And at the end, the initial state and the final state is basically the same, very similar. But for the loose packet bed, initially there is almost a constant density in the bed. So this is a constant density. And as you compact the system, there is the density inversion, but at the end, the system becomes hydrostatic. So there is this final configuration again is very similar in both cases. To characterize the hysteresis in the system, we measure the instantaneous net displacement of particles. That is basically the difference between the position of the particles at a given time minus the initial position of the particle. So as you can see here, for the standard bed, this delta R increases, and then increases reaching a maximum when the maximum compression is reached, and then decreases during the expansion, and at the end the value of D is practically is 2. That is very well. The difference with the initial value 0 is very small. No, but for the loose bed, you can observe that there is a huge difference between the final net displacement of particles compared to the standard packet bed. This is a snapshot showing the motion, the trajectories of the particles that show that the particles that basically move are at the top, close to the piston, while at the bottom the particles practically don't move. And this is because the magnetic repulsion between the magnets decreases very fast. It decays as a power law to the -4 for the case of magnetic repulsion. So also we can measure the mean interparticle distance and we can observe here that this mean interparticle distance is minimum when the maximum compression, but it's very similar for the loose and the standard bed. In fact, it's more symmetric for the standard bed, which indicates that there is less hysteresis in the system for the case of the standard packet bed compared to the loose packet bed. Okay, but the important thing that we wanted also to analyze is how the force, the compression, the force load or the resistance to compression is versus the piston stroke, as in the previous experiments. So as you can see here, in this plot is the force versus the piston stroke. For the compression, you have the different curves. The red one is for the loose packet bed. So as you compress the bed, the force increases. up to reaching a maximum force, and then decreases following the red line, the red curve. But for the loose packet, this is for the loose packet bed. For the standard packet bed, the compression starts when the piston stroke is larger, because the bed is more compacted. But then they follow during the compression a different curve. They reach a maximum at the same moment, and then they follow the same expansion curve. So this is here you can clearly see the hysteresis again in the system, related to this magnetic granular material. And it is independent of the compression rate for the values studied in this experiment. So we varied the compression rate from 1.5 millimeters per second to 8 millimeters per second. And we observed that it's independent, the force versus the piston stroke is independent of compression rate in all cases, for both the loose and for the standard bed. This is only the compression case, the compression phase. So in all cases, you see that for the loose, for all the compression rates, the curves follow the same trend, and for the standard bed also follow the same trend. And in both cases, if you put the log linear plot, you observe that they follow an exponential increase of the force versus the compression stroke. Well, for the relaxation phase, I haven't discussed this during this talk, but in all cases, for all the materials, it's basically well described by a Maxwell model with two exponential terms, with different time scales, with two different time scales. This model is able to describe well the compression force versus the piston stroke. Okay, Yuri and his student performed numerical simulations trying to reproduce the experiments. So they use they consider the magnetic force acting between the particles and with the walls. They consider the weight of the particles. And another term that is important here is the friction force. So by putting all these expressions, for instance, the magnetic force, well, this is the magnetic dipole of the particles. So this is the distance between two particles. And then they have this dependence, this is to the -4. And with the particle wall, you also need to introduce the dependence between the force that is experienced by each particle due to the magnetic wall, and also the friction force. But for the friction force, we propose two models. One that is viscous friction model that depends on the velocity, and dry friction model that does not depend on the velocity. So this is the case of snapshots with the numerical simulations that qualitatively describe well the standard packing case. As you can see here, there is a maximum compression. The color indicates the magnetic pressure acting on the particles. So the more yellow the particle is, it means that the larger is the magnetic pressure acting on this particle due to the rest of the particles. You can then, from the numerical simulations, obtain this kind of information that cannot be obtained from the experiments. Qualitatively, we obtain the same results as in the previous. We show this density inversion also during the numerical simulations, and also that the trajectories, that the particles at the top are the larger trajectories, and that the particles at the bottom basically don't move during the compression. But unfortunately, from the numerical simulations, well, we have performed using the viscous friction model, where you observe that the force during compression depends on the velocity, something that is not observed in the experiment. So the viscous friction model is not able to reproduce experimental results, but the dry friction model that doesn't depend on the velocity. So you can see here that the compression and phase and the relaxation follow similar trends to what we observe in the experiments. So the dry friction model is able to reproduce qualitatively well our experimental results. Here is a comparison between the experimental results, and while the dry friction model is able to reproduce the experimental results, we can see that quantitatively there are important differences between the experiments and the numerical.
Felipe, are you there? Can you hear me? Can anyone hear me?
Yes, I can.
Yes,
Yes.
I can hear you.
Yeah, so it's probably Felipe. Let's wait a little bit. Yep. Felipe, are you there? You're muted.
I'm sorry, there is an internet connection here, a problem, and
Okay.
I lost connection.
Let's try again then.
Are you there? Can you hear
Yes,
me?
we can hear you. Go ahead. Yes.
Hello?
Yes. Well, you haven't shared your screen yet.
I'm sorry. Yeah, there is an interconnection, so a problem. Can you see my screen now?
Yes, it's back. Yep.
So I'm sorry, I don't know where did you lose my presentation.
Yeah, we can see your presentation now, so carry on.
Yeah.
We've seen that you were discussing the forces. You were discussing the last graphs.
Yeah, this one.
Yeah,
right?
this one. Yes.
Yeah. So the point here is only that from the numerical simulations, we have not been able to describe the experiments, at least only qualitatively, but there are important discrepancies between the experiments and the numerical simulations. And we presume that these differences are related to the friction force model that we are using in this system. Because, for instance, we are not taking into account that the force caused by the particles in the pistons are, that the walls do not interact with the piston. The walls also are repulsive, and we are not considering the interaction between walls and the piston. And we are also assuming magnetic interaction of particles with an infinite bar, while the bar is finite in the experience, obviously. So there are some discrepancies, and we are trying to work on this to improve the numerical simulations to be closer to the experimental results. Well, this is what I wanted to show. I have some final. So I want to, to finish, I want to acknowledge the people that has been helping in these experiments, Tomomi Omura, Hiroaki Katsuagi, that we're working basically in the hierarchical granular matter compression. It's a collaboration with them at the University of Nagoya and Osaka in Japan. And for the experiments that are related to the compression of magnetic particles, where we are working all together also with Stefan Dorbolo, George, and Yuri Dumare-Sogar. So thanks for your attention, and if you have questions, well, please.
Thank you very much, Felipe. It's very nice talk. Do we have any questions? I have a question for you, Felipe, on the dry compression experiments. You've tested the grains and the glass beads and sand, right? And the very first ones.
Yeah.
And you showed that there is a major difference on the force dependence, one that has an exponential scaling, and the other one has a power law scaling. Why do you think this is the case? What is the physical reason behind these two different behaviors? And the second question is still related to that. Does friction coefficient and friction overall, including there on this friction, particle shape and all the mechanisms that can influence friction, be the reason behind that?
Yeah, well, we believe that the mainly difference is that, of course, those particles are compressed, they are soft, so you can deform them before crushing or before moving the particles and deform them. While the glass beads, they are, they are rigid. So the deformation of the glass beads is basically for this amount of applied stress, the deformation for glass beads is negligible compared to those particles. So the reason why the power law increases slowly than the glass beads, the force for the case of those particles increases at power law, while for glass bead is exponential, could be related to this different nature in the composition of the particles.
I see.
The softness of those particles. We believe that this is the main reason. This is why you have an increase, then you have an undulation that decreases the force instantaneously, and then you start increasing again. So we believe that this is the reason. And the second question was related to what?
Friction coefficient.
Yeah, so the friction coefficient here, well, it must appear somewhere in this F star coefficients. No? We haven't analyzed, that depends on the friction coefficient. We haven't changed, for instance, the wall roughness, as in the case of the experiment performed by Eina and his group. So we didn't perform this kind of analysis yet, but we believe that it should be that information in this kind of coefficient.
I see. I have another question. So do you think so? Go ahead.
I'm sorry. No, continue. There was another question also from the.
Okay, all right. So let's see. Is there a question from the audience? Okay, no. So Felipe, when you change from dust to glass particles, you are also changing the size of the particles, right?
Sorry. I'm sorry. I'm going to stop sharing, and then we can.
Okay. All right. So you when you showed both dust and glass beads, they have different sizes, don't they?
They have they have different sizes. We work with different sizes, but we compare particles of the same size. Those particles with the same size of glass beads. Yeah.
Okay, and then the same size of agglomerates.
Yes, exactly. The same size of agglomerates with the same size of particles.
I was going to say whether there was a size effect problem issue there.
Yeah. In fact, the main difference, the main role of the grain size is the size of these oscillations. Also, the size depends, the oscillations and also the force drops depends on the grain size. So this is the main role. But in both cases, for the dust particles, you observe undulations as you increase the grain size, and for the case of glass beads, you observe sudden force drops that also increase in size with the glass bead size. So this is the main role of the particle size.
I see.
I'm sorry, I didn't put the video, the camera, but the internet connection is very bad.
No worries.
So I'm sorry.
That's absolutely fine. Okay, so I think we've come to the end of our Granular Materials Day. I'd like to thank you all for attending. It was a great day. Thank you so much. It would be nice to see you all and maybe take a screenshot of those who are here. If you can just switch on your camera and say, wave your hand while I take a screenshot there. Okay.
Thank you a lot.
Thank you. It was very nice meeting you all. It was very nice. Nice to see you all. Thank you for being awake so late or so early, depending on your time zones. It was anyway nice to see you all. Thank you. Hope to see you again at some point. Bye-bye. Thank you.
Bye.
Bye-bye. Thank you.
Thank you. Bye-bye.
Bye-bye.
Yuri, thank you so much.
Bye. Thank you.